All right, let's just jump right in. I want you to picture something incredibly simple. Imagine you're holding a solid stone in one hand and a glass of water in the other. If you drop that stone, it just falls straight down, right? It totally maintains its exact shape. But what happens if you pour out that glass of water? It spreads, it splashes, and it completely takes the shape of whatever it hits. That fundamental difference between a solid object and a flowing substance is exactly where our journey begins today.
Welcome to This Explainer. Today, we're taking a masterclass on the foundational concepts of fluid mechanics, drawing directly from the highly structured classroom lectures of civil engineering expert Professor Nirmal. We're going to build a rock-solid, academically rigorous understanding of what fluids actually are, and more importantly, the specific mathematical properties that govern exactly how they behave in the physical world. Here's our agenda for today. First, defining a fluid. Second, 4 core fluid properties. Third, calculating fluid properties. Fourth, understanding fluid viscosity. And fifth, real-world engineering applications.
So, let's start with part 1, defining a fluid. Think back to that stone and the glass of water. The definition is actually elegantly simple. A solid has a fixed, definite shape. It actively resists deformation. But a fluid? A fluid is a substance that has no definite shape of its own. And crucially, it's capable of flowing. It will absolutely always conform to the boundary of its container. And this brilliantly illustrates the broader science we call fluid mechanics. This whole field is systematically broken down into 3 distinct areas of study. First, there's statics, which examines fluids at rest. Think of the immense, quiet weight of water stored inside a massive municipal water tank. Second is kinematics, which deals with fluids in motion without considering the forces actually causing that motion, kind of like analyzing the flow patterns of a rushing river. And third is dynamics, where we look at fluids in motion along with the forces involved, like the massive kinetic energy of water violently hitting a hydroelectric turbine blade. Now, a super common question we get at this stage is, do gases count? The answer is absolutely yes. Because a fluid is defined as any substance capable of flowing with no definite shape, this perfectly encompasses both liquids and gases. The main distinction you need to remember is that liquids, like water and oil, are mostly incompressible, meaning their density really doesn't change much under pressure. Gases, however, like air and steam, are highly compressible, but physics treats them both as fluids simply because they both flow. Moving right along to section 2, 4 core fluid properties. Before we get to the core formulas, we have to categorize these properties. In physics, properties basically fall into 2 fundamental buckets. Intensive properties do not depend on the amount of fluid you have. Whether you're looking at a single drop of water or an entire ocean, intensive properties like temperature, pressure, and density remain completely constant. Extensive properties, on the other hand, depend entirely on the amount of the fluid. These scale with quantity. Examples include total mass, momentum, and total volume. So let's dive into our first and arguably most foundational intensive property, mass density, represented by the Greek letter rho. The formula is beautifully straightforward. Density equals the mass of the fluid divided by its volume. In standard SI units, we express it in kilograms per cubic meter. To give you a mental benchmark, standard water has a mass density of about 1,000 kilograms per cubic meter. It's essentially a measure of just how tightly packed the matter is within that specific volume. Next up is specific volume, represented by a lowercase v. This is simply the reciprocal, or the exact mathematical inverse of density. It's the volume of the fluid divided by its mass, or simply 1 over rho. The unit here is cubic meters per kilogram. Now, what's really interesting is knowing when to actually use this property in the real world. While civil engineers use mass density all the time for liquids, specific volume is primarily applied in thermodynamics, specifically when you're dealing with those highly compressible gases we mentioned earlier, like air or steam. Our third core property is specific weight, denoted by the Greek letter gamma. This is defined as the weight of the fluid divided by its volume. Now, because weight is simply mass times the acceleration of gravity, this formula neatly simplifies down to density, or rho, multiplied by gravity, g. It's expressed in newtons per cubic meter. The absolutely crucial point here for any future civil engineer is that specific weight is the direct tool you use to calculate fluid forces, because force is derived from weight. For water at standard conditions, gamma sits right around 9,810 newtons per cubic meter. And our fourth property is specific gravity, represented by the letter S. This one's a little bit different. It's a dimensionless ratio, meaning it literally has no units at all. It simply compares the density of your given fluid to the density of a standard reference fluid. For liquids, that reference is always water. For gases, it's air. If a liquid has a specific gravity of less than 1, it means it's lighter than water.
And this brilliantly explains why cooking oil, which has a specific gravity of roughly 0.9, forms a distinct layer and floats perfectly on top of water in a glass.
Okay, let's jump into section 3, calculating fluid properties. Let's walk through our first example together. Imagine we have exactly 1 liter of gasoline, and we're told its specific gravity is 0.7. Our goal here is to find its density, specific weight, and total weight. First, we need a quick unit conversion. Remember that 1 liter is equal to 0.001 cubic meters. Okay, step 1, find density. We take our specific gravity, 0.7, and multiply it by the density of water, which is 1,000. That gives us a density, or rho, of 700 kilograms per cubic meter. Step 2, find specific weight, or gamma. We take that density of 700 and multiply it by gravity, 9.81. That gives us 6,867 newtons per cubic meter. Finally, step 3, find the total weight. We multiply that specific weight by our volume of 0.001. That leaves us with a final weight of 6.867 newtons. See? A simple, logical, step-by-step calculation. Now, let's try reverse engineering this relationship. Suppose we have 1 liter of a completely unknown liquid, but this time we measure its weight directly. Let's say it weighs exactly 7 newtons. How do we find its specific gravity? Well, step 1. We start by finding the specific weight. We divide that 7 newtons by our volume of 0.001 cubic meters. That gives us a specific weight, gamma, of 7,000 newtons per cubic meter. Step 2. We find the density. We take that 7,000 and divide it by gravity, 9.81. That yields a density of 713.5 kilograms per cubic meter. And finally, step 3, to find specific gravity, we simply divide our new density by the density of water, which is 1,000. That gives us a specific gravity of 0.7135. This really proves just how deeply interconnected these foundational properties are. If you have just one piece of the puzzle, you can calculate all the rest. All right, section 4, understanding fluid viscosity. To intuitively grasp this next concept, I want you to do a quick mental experiment with me. Imagine you're holding a spoon and stirring a glass of tap water. It moves really easily, right? Very little resistance. Now, imagine putting that exact same spoon into a thick jar of honey or a heavy barrel of cooking oil and trying to stir it at the exact same speed. It's significantly harder. So why is that? The scientific answer is viscosity. Formally defined, viscosity is the property of a fluid that offers resistance to the movement of one layer over another adjacent layer. Honestly, the easiest way to think about this is simply as internal friction. When you stir a fluid, you are literally forcing layers of that fluid to slide past one another. The thicker the fluid, the higher the viscosity, and the stronger that resistive force actually is. This core concept is the precise foundation for Newton's law of viscosity, which becomes a major structural pillar when you get into advanced fluid dynamics.
And finally, Section 5, Real-World Engineering Applications.
First, let's just quickly review these core concepts. We've got mass density, specific volume, specific weight, and specific gravity, all with their exact mathematical formulas and standard SI units. This isn't just a list to blindly memorize. It's a foundational tool set. Whether you're studying flow in pipes, pressure on retention walls, or complex thermodynamics, every advanced topic you encounter from here on out will rely heavily on these precise formulas. And here is exactly why they matter in the field. These are vital tools used every single day by civil engineers. When designing a municipal water supply pipeline, engineers have to use density and specific weight to accurately calculate the pressure acting at different points across miles and miles of pipe. When they're constructing a monumental structure like a hydroelectric dam, they use specific weight to calculate the immense, almost unfathomable total force of the water pushing constantly against that concrete wall. And when an industrial facility needs to select a pump, they look directly at the specific gravity of the liquid to determine exactly how much mechanical power is required to move it efficiently. I want to conclude this explainer with a really fantastic piece of advice straight from Professor Nirmal's lecture. Fluid mechanics is not a subject to memorize. It is a subject to understand. Observe the world around you and you will see fluids everywhere. So here is your takeaway challenge for today. Later on, when you encounter a fluid, whether you're pouring milk into your coffee, using cooking oil for dinner, or just turning on the tap, take a second to actually ponder it. What's its density? Is it heavier or lighter than water? Why exactly does it flow the way it does? Because the more closely you observe these everyday phenomena, the more those incredible engineering secrets will start to reveal themselves to you. Keep observing and keep learning.